This is an instructional video for your 4.4.3 lab, which is on radioactivity and radiation. So this little summary just talks about how you're surrounded by different types of radiation. It's constantly entering Earth's atmosphere. Luckily, most of it is absorbed, mostly by the ozone layer. A fraction reaches the surface of the Earth. Okay, some rocks, like granite rocks, have naturally have radioactive materials in them. This radiation is caused by the radioactive decay of unstable elements that make up the rock. So you can use a device called a Geiger counter, and that measures how much radiation an object emits. All right. So in this lab, you are looking at half-life. Okay. So if you remember, half-life is the amount of time it takes for half of an unstable or radioactive isotope to decay. So how long does it take for half of it to be gone and converted to a different element and half of it to remain? Okay. You will have to start with your pre-lab. Okay, so if we look at the pre-lab real quick, has questions. How is a radioactive element different from a stable element? What happens to a radioactive element? And what information can it tell you? Here is a scenario. Imagine that a radioactive isotope has a half-life of 2 years. So that means every 2 years, half of the number of atoms will decay. And so you'll just complete this very simple table, cutting the number in half each time. Okay? And then question 4 just gives you a graph to read. The question is, according to the graph, what is the half-life of carbon-14? Okay? So how long in years, in this case, does it take for half of a sample of carbon-14 to decay? So you're just going to simply read the graph and answer that question. Fairly simple. The lab itself is here. Okay. Goal is to understand that a very large number of random events becomes predictable, perform a simulation of decay, and observe how a radioactive daughter product behaves. Okay, so here you're using small cubes and spheres. You are not using any materials. You're doing the dry lab, of course. This introduction is helpful. It tells you about half-life. It tells you what a daughter product is. And it tells you what you're going to be doing in this experiment. You're big boys and girls. I'm not going to read this to you, but I do expect that you read through this so you have a little bit of background knowledge for why you're doing what you're doing. Okay. The next thing you will see in your lab is this giant data table of data that they have collected. Okay. So if you look, you have the trial number here, 1 through 20, the number of dimes remaining. So the procedure, if you kind of want to know what do you mean dimes remaining, you're going to look at the cubes and observe that they have dots on 6 sides. The side with 2 dots will indicate the cube has experienced radioactive decay. Count out 50 dimes and place them in the cup. Holding one hand over the cup, shake the cup and pour the dimes onto the table. Count and remove the dimes that landed with their heads facing up. Okay, so what you're doing is separating heads from tails to kind of simulate decay. All right, so you start with 50 dimes, and then you have 28 that have not decayed or are remaining. Then you have 13 after 2 trials. Then you have 7, and so on and so forth. Okay, and then there's some data for the number of cubes and some data for the number of spheres. And the first question says, use your graph paper to plot a graph of the number of remaining dimes versus the number of throws. Okay, I'm going to show you how to set up your graph right now. Okay, here's how you're going to set up your graph. So you'll notice on the y-axis here, I have the number of whatever it may be, number of dimes, number of cubes, or the number of spheres. you're going to be graphing all 3 of those on the same graph, okay? And then down here on the x-axis, I have the number of throws, which is the same as the trial number. So I would advise you to make your graph just like my graph, because this will accommodate all of your data, and it will spread the line out nicely over the entire graph. So I did the lines going in the y direction by 5s, 5, 10, 15, 20, 25, 30, etc. And then the lines going across, I did by 1s, because I only needed 20. Okay, so if I'm looking at my data for the number of dimes remaining, I'm just going to plot a couple of the points for you. So you want to make a legend. So I'm going to say, for me, red will be dimes, right? And I know I'm going to have to graph the other ones. So I'm going to make blue be the cubes. And I'm going to make that's too close to red. I'll do green be the spheres, okay? So that you can distinguish them. I'll go back to red. I'm looking at the data that was given to me in the lab, and it says for trial number 0, I have 50 dimes, right? So I'm going to go to trial number 0, I'm going to go up to 50, and I'm going to plot a point. My next one is 128, right? So I'm going to go to 1 over, move 1 over here, okay? And then I'm going to move up to 28. So this is 25, this is 30. So I'm going to go somewhere in between there. And I'm going to mark my next point. The next one is 213. So again, I'm going to move 1 more over for 2, and then up to 13, which is between the 10 and the 15 line. And I will mark a spot there. Okay, so you'll continue to do that for all of the data for the dimes, and then answer those dimes questions, and then come back and plot your cubes and spheres. So hopefully this graph setup will expedite your graph creation process. Okay, we're back. The second question says, what is the half-life of the dimes according to the graph? So just like you read a graph in your pre-lab to predict half-life, you're going to do the same thing here with the graph that you just made. Since the chance of a dime decaying is 1 in 2, what should the theoretical half-life be? How does this graph simulate a decay graph? So these are all conceptual questions you should be able to answer. Okay. Number 5 says, on the same graph, use a different color and plot the number of remaining cubes versus the number of throws. So you're going to go back up. On the very same graph you made your first line, you're going to now graph in a different color the number of remaining cubes, this middle column, versus the trial number. Okay? So this is a typo. This should say, starting with 50 cubes, redo the experiment, replacing cubes with spheres when the cube lands on 2 dots. Stop after 10 trials, record and graph the results. So you have some sample data below question 10. This is the sample data for question 6 that you're going to be using. Okay, starting with 50 cubes, going all the way down to 10 trials. All right, and then you're going to be answering these questions. If you're in the midst of your lab and you don't know what to do, just shoot me an email. We can jump on and work on it together. Okay?